So we made a motor body, we put it on our video. What I tried to do is to make slightly more permanent motor. And I'm going to try and see if I can get it to run. You see, the battery is just about died. There, it's going again. Okay, so just, if you've seen, you can go. Just come and have a look. So this has got two magnets, it's got a matchbox with some coils around it. We've got our brushes and our armature. And with a sufficiently powerful, it's working.
So what's supposed to do this? What are you going to do with this, sir?
We did a whole session on motors. Did you not? You were not here. Electrodynamics. Next people come and have a quick look. Next people just come and have a quick look. Okay. Just about. As the hotter it gets, the... Anyone not seen it? Okay. For the benefit of those of you who weren't here, let's all sing it. And for the benefit of those who were here, let's all sing it. My split ring makes me behave like a DC wave, like a DC wave. My split ring makes me behave like a DC wave. Great. So that's a DC, it's got a split ring, and it's got a wave function that looks like this. Then there's this part 2 to the song. My slip rings, and you do this, you make a ring, any way you like. My slip rings make me behave like a sine wave, like a sine wave. So let's sing that second part. My slip rings make me behave like a sine wave, like a sine wave. Kyle and Pascal, we're doing this for you, so please participate. Okay? So my slip rings make me behave like a sine wave, like a sine wave. Let's do it once more for those who didn't do it. Okay? My slip rings make me behave like a sine wave, like a sine wave. Great. Now, if we take this motor, it's a DC motor, it runs off a battery which is DC. It's in simple form looks like this. What are those two things called? They're called, begins with a C, the commutator. Then the commutator rubs against these little wires that stick up. What are they called? What are those little things called? Begins with a B. Brushes. This thing is called two names. What is it called? A or C? It's called a coil or an armature. Then we've got, what is this thing here and what is this thing here? What is that? It's a magnet. Okay. So there is our motor that we made. Now, if it's a DC motor and I go time in seconds, voltage in volts, and I go over a period of time, what happens here? Does it go down or does it go up? If it's DC, then it goes up and it does this. Every time it turns, it makes 2 camel bumps, like a dromedaris camel. I believe those are the ones with 2 humps. But I could be wrong. I do not know my camels as well as the Middle Eastern people. So this represents here 1 turn. Okay, now here, folks, is 80% chance they're going to ask you this in the exam. And here is the question. Does the top of the bump occur when it looks like that, or when it looks like that? Simple question. Ask you to say, does this, when it's standing up, produce maximum voltage, or when it's lying horizontal? And what is the answer? Is it when it's standing up? Do you see how that coil is turning? For those of you who've just seen it, this thing can stand like that or like that if our magnets are here. Now it's generating a voltage there, maximum, or there, maximum. Let's take a vote. Who says hump it now? Okay, even some of the people who weren't here have guessed the answer. Who says the maximum hump is there? The maximum peak voltage. Democracy rules again. What did we call this maximum hump? V max, right? You remember that? You remember max? Okay, does V max go here or here? And the answer is here. Well done. Because it cuts the field line. Now, why is it not cutting the field lines like this? So look what it's doing. It's there. It's stroking the field lines, but it's not cutting them. Correct. Now watch here. It's cutting my fingers. Do you see the difference? Stroking, cutting. Field lines. Stroking, it's not breaking them, it's rubbing them. Here it is cutting the field lines. Every time you cut a field line, you get a push on the electron, you get a voltage. So, here's the question I'm going to ask you. At this point, is the arm to draw the armature at this point. So how are we going to draw it? Up or vertical? Vertical, horizontal, at this point here. It's vertical. So I hope you're a good drawer. That's how you draw it. How are you going to draw there? You're going to draw it horizontal. Like that. How does it look there? Vertical again. This diagram comes up every year. What's it going to be there? And there is one complete turn. So it's turned one complete turn. And there we go. Make sense, everybody?
So what's the reason for that? Is it because it cuts the field line?
And it comes down to when it's in the horizontal position, it's cutting the field lines. Because the field lines go like this. And when it's up top here, it's just doing this to the field lines. It's rubbing them. It's not cutting them. When it's horizontal, it's cutting the field lines. And then you can say which law tells that if you cut field lines, you get a voltage.
Faraday's law?
And that came from Faraday's law, which E equals. I know that Ezra knows it. Yeah, you know it.
What is it?
Is it negative?
MC squared.
Negative is
Delta phi of the T.
the change of field length over the change of field length.
There we go.
Yeah, everybody.
Lovely. And
I don't know the name of the song.
who can elaborate on what phi is made up of? I bet I can ask almost anybody who was here what phi is made up of. Two things. This here equal to phi is equal to A plus or AB. And what is A? The area. Now if you get another magnet, have you got a bigger area?
Yes.
So adding magnets increases the area. If you've got a strong magnet, you've got more field lines. That refers to B, the number of field lines. And then delta T. The quicker I spin it, the bigger or smaller the voltage. The bigger or smaller?
The bigger.
Let's take a vote on democracy. Who says the faster I spin it, the bigger the voltage? Hands up. Okay, you all know it. Well done. So the less lazy you are, the bigger. Now, the faster I spin it, is the bigger or the smaller this?
The faster is bigger.
The smaller or bigger is that?
Repeat the question, sir.
The faster I spin it, the smaller is delta T.
The bigger.
How much time changes when it spins fast? A big time?
A
A little time, like over 100. 1/100th of a second it spins, right? So the smaller that, the bigger that. Why? Because it's an inverse relationship. And for those who are mathematically inclined, what is the denominator of 1 over 100 equal to?
0.00.
It's equal to,
0.00.
it's a new time, 100. Do you know that by saying 1 upon 100 is equal to 100. 1 upon 100 is equal to 100. Because when you take that and you put it on the top, it becomes inverted, it becomes 100. Do you remember that? So the smaller your denominator, the bigger your numerator. So the faster you spin it, the smaller the time, the bigger the voltage.
You want the answer?
Who can say that for me? The faster I spin it, the time?
The smaller the time,
The smaller the time,
and the bigger the
the
energy.
bigger the
Energy.
voltage or the energy. Okay. So what is the question they're going to ask you? They're going to ask you this question. You will find it in your little notebooky thing. Okay, you will find it. You will maybe find it in your textbook as well. But if you look in that notebook thing, you will find this exact drawing. Please note. I will give you the things you need to know. Okay, so now we've revised the photoelectric effect. We've revised the electrodynamics. We're doing the practical. Any other questions before I go on to a new section? Say that again. I can't hear you. Yes, we can make our own electricity by spinning this. What type of electricity, AC or DC, will I get by spinning this? I will get DC. You know what I'm tempted to do? But I'm just not going to be bothered to do it. I'm tempted to spin this, attach it to a galvanometer. Remember that big thing that moves? And as I spin it, the faster I spin it, the more it will move away to the one side or the other. But that relies on us getting a good contact. And I'm not sure we're going to get the best of contact. And I think we've done enough practical work today.
You what? I didn't know
Okay,
So maybe they chemistry?
you ask a very good question. We're going to do chemistry right now.
Why is that one?
We are not finished with physics, but we have covered physics. Thank you. We have covered the basic physics syllabus. It was not hard. I did not find it at all challenging. If you found it challenging, that is fine, but you will find that this stuff is easy peasy. Even this question you did today, come on, you do it once, it gets boring. So, I don't know whether you found any of this challenging. How many found this very challenging, the electrodynamics and the photoelectric effect? Or did you find it copable? You could cope with it. Copable? Easy enough? Okay. Do you want to go over this again?